This example has a lot going on in it, and in fact, this may be the most difficult, most involved problem in the unit, and yes, it appears this early, so please try to stay focused with what is going on in this lesson because it is important for you to be able to solve the harder problems. So let's see what we have here. We have 3 blocks, a 5 kilogram block, a 10 kilogram block, and a 20 kilogram block. We have 2 pulleys, right? We have a pulley here and a pulley here. We have 2 strings or 2 ropes. We have what I am going to call string A here going around our ideal pulley. So remember, our ideal pulley is really, for us right now, nothing more than a frictionless cylinder and the rope slides across it, so I'm going to call this string A. So the tension in string A will be the same, one string, one tension. We are going to have a second string connected to a hook to the 5 kilogram block, passing over this pulley to the 10 kilogram block, and I'm going to call that one B. So one tension in string B, but we cannot assume that the tension in string B equals the tension in string A. So one string, one tension, 2 strings, we cannot assume that they have the same tension. Okay, I'm going to erase this to clean my page back up a little bit. And when we look at doing our analysis of a complicated system, we're going to focus on individual objects, do complete force diagrams for them, and then try to structure a system of equations. In other words, have 3 equations, 3 unknowns, 4 equations, 4 unknowns to problem solve the problem. And with the help of our calculators and a little bit of linear algebra, we'll see that we definitely can do that. All right. We have friction in this problem. So as I said, there's a lot going on. We have friction between the 5 and the 10, and the friction between the 10 and the table. And in this case, we are told that the coefficient of friction is the same between all of the surfaces, and the static coefficient of friction is the same as the kinetic coefficient of friction, which is not normally the case. Normally, the static coefficient is bigger, and then when it breaks loose, the kinetic coefficient is a little bit smaller. But in this case, we were given the same 0.25 for all surfaces, so that is what we're going to do. We're told to draw separate force diagrams, so we're going to do that. And ultimately, we're looking for the tension between the 5 and the 10 kilogram block, so that's what I called tension B here. So remember, that was string B. And we'll see how to do that after we get our system of equations. So the first thing you really want to do, even before doing your force diagrams in terms of your analysis, is to take friction out of the problem for a moment and visualize how the system is going to move. So any of the problems that have friction, we're first going to think about what would happen without friction. Well, if there's no friction in this system, the 20 kilogram block definitely goes down. The 5 kilogram block definitely goes to the right, and the 10 kilogram block definitely goes to the left. Those directions are going to be important because when we include friction into the problem, we're going to have to have friction opposing those tendencies for motion. So let's get started and let's talk about our force diagrams. Well, the first force diagram we have here, I'm going to start on my right and work backwards. I'm going to start with the 20 and then go to the 5 and then to the 10. The 20 is pretty straightforward. We have a 20 kilogram mass. Gravity is 9.8. We get 196 newtons gravitational force pulling down on the 20 kilogram block. Well, we said tensions pull, never push. So we have the tension in string A pulling up on the 20 kilogram block, and that is it. Our force diagram is complete for the 20 kilogram block, and now we are going to move on to the 5 kilogram block. On the 5 kilogram block, we have tension A, same string, pulling to the right on the 5 kilogram block, because we said with no friction, right, the 5 kilogram block is going to go to the right, and that means when we put friction in, as we did here, friction has to go to the left on the 5 kilogram block, opposing the motion. But we also have the string B attached to the 5 kilogram block. So string B will be pulling back or to the left on the 5 kilogram block, fighting the tension A to get block 5 to go to the right. Okay, so block 5 is sitting on block 10, so we have one more force, so we're going to assume that block 5 doesn't sink into block 10, so we have a force normal pointing straight up here, and notice that we were pretty much immediately able to plug in some values here, so let's talk about where these values came from. So we have the 5 kilogram block, and 9.8 gives us a 49 Newton weight force, and without any other forces in the y direction to either increase the downward force or decrease the downward force if it were another upward force, we immediately now know that the normal force does have to be equal to the weight force, 49 newtons. So there has to be a normal force on 5 by 10, keeping block 5 from sinking into the ground, and that has to be 49 newtons. Well, since we know that friction is mu times the force normal, we can also automatically get the frictional force, mu times the force normal, where we know the force normal is 49, so when we do 49 times 0.25, we get our 12.25, which is shown here. And that is it for the 5 kilogram block. That's all we can do. So we have 2 out of the 3 done. Let's get this 10 kilogram block done in terms of identifying all the forces and putting in whatever values we can and get on to solving the problem numerically. Okay, so without friction in this problem, we said that the 10 kilogram block would go to the left, right? Tension B will pull it to the left, and if there's no friction, it would have to move in that direction. So that means whatever friction is in the problem at all, we'll have to oppose that motion, and in this case, we'll have to go to the right. So the friction between the 5 and the 10, and the friction between 10 and the table, will both have to go to the right, opposing the motion or tendency of motion for that 10 kilogram block to the left. And let's talk about what numbers now we can get into the problem based on what we know about block 10. Well, we know the mass of block 10, so we know 10 times 9.8 gives us our 98 Newton weight force. We have to be a little careful here. Notice that I don't have the normal force equals 98 in this case, the normal force on block 10 by the table. And that is because we still have block 5 sitting on top of block 10. So block 5 hasn't disappeared. I put it in a little dash here just to remind myself it hasn't disappeared. It's still there, but I'm focusing on only the forces acting on block 10, so I don't actually draw it in. But we still know Newton's third law, action-reaction pairs. So we saw from our 5 kilogram block there was a force on 5 by 10. That means there had to be a force on 10 by 5, equal magnitude, opposite in direction, and that's the 49 newtons we have here. So when we look at the normal force on 10 by the table has to not only support the 98 Newton weight force, it also has to support that additional force pushing down on block 10 of 49 newtons. So that is where the 147 comes from, and I'm going to put that in here explicitly for you. The 147 comes from the 98 newtons plus the 49 newtons, giving the 147 that the table has to support. And now we are all done. Our force diagrams. We can go into generating equations from F equals ma, and what we're going to do is look at the sum of the forces in the x and y direction for each of the objects individually, and then we're going to see if we have enough equations and enough unknowns. So looking at the 20 kilogram block, we have tension A going up, so that's why that's positive. The weight force, negative 196. Negative goes down is my negative direction. And notice sum of the forces equals mass times acceleration in the y direction. I included negative A here. This is really important. You have to determine the correct direction for the acceleration in your equation, and we knew that by imagining the motion without friction, that we had to have a negative acceleration here. If you leave that as a positive acceleration, you will not get the right answer when you go to solve it numerically in your calculator. Okay, my page here, just so you can understand what you're looking at. My 5 kilogram analysis is here, and then my 10 kilogram analysis is on the left. So the 5 kilogram block in the x direction has tension A to the right, tension B to the left, the frictional force between 5 and 10, contributing the 12.25 Newton frictional force to the left as well, equals mass times acceleration. And here I do leave the positive with the acceleration, because in this case we said without friction it has to go to the right. In the y direction, there's not much here to really help us. Some of the forces in the y direction equals 0, so that means that the force normal had to be 49, and then when we did mu times the force normal, we got our frictional force. Okay, the 10 kilogram block. The 10 kilogram block in the x direction has both frictions going to the right, so that's why they are positive 12.25 and 36.75. Where did that come from? Well, that's friction. That's mu times the force normal, and you can see I have it down here. The force normal, remember, is the 147 between the table and block 10, so that's where we get the 36.75 from. And we have the tension in the string to the left, so that's why that's negative. And remember, we said without friction, the 10 kilogram block also moves to the left, so that's why that's negative. And that is it in terms of equations and unknowns, because we have the 1, 2, and 3 that I have circled here. 3 equations, 3 unknowns. Tension A is unknown, tension B is unknown, and the acceleration is unknown. So those are my 3 unknowns, and you will be able to solve them by watching the YouTube video and utilizing the matrix on your calculator. I'm going to erase all this out here because I'm going to show it to you again. I'm going to erase this. And you don't need to copy this into your notes. Once you have the 3 equations and 3 unknowns, this will help you when you watch the video, however. So to get the equations into the form you need for your calculator, you're going to need to line up all the variables in columns and then have just a numerical answer as the last column. So that's what I'm going to show you quickly here. So you would need to rewrite this first equation, and my negative A did not magically become positive. I multiplied through by a negative, so that's why it's positive 196 negative TA. So, and you didn't have to. You could have left it as it was in the equation up here. I don't know why I multiplied through by the negative, but I'm going to leave it and let's go with it. So here I have negative 1 times tension A plus 0 times tension B minus 20 times the acceleration equals 0. And you'll see how this game is played in a moment. Here we have 1 times tension A minus 1 times tension B minus 5 times the acceleration equals positive 12.25 when I bring it over the other side. And here we are going to have 0 times tension A plus 1 times tension B minus 10 times A, and this is the 12.25, and the 36 gives us 49. So there is my 3 by 4 matrix. So the first column is going to be negative 1, 1, 0. The second column is going to be 0, negative 1, 1. The third column is negative 20, negative 5, negative 10, and then the fourth column is going to be 0, 12.25, and 49, and then the YouTube video is going to show you how to plug that into your calculator. We are also going to talk about it in class, so you don't worry about it if it doesn't work out for you the first time. We can correct that in class. But if you've done everything correctly and you go to solve that determinant with your row-reduced echelon form, it's a linear algebra thing, you should get that the acceleration is 3.85, the tension A is 119, and tension B is 87.5. So I do realize there was a lot going on this page. Hopefully it was clear or clear enough that you can ask questions in class or get your questions clarified and come from them with a basic understanding of what the approach here is supposed to look like.